starting. So today we have for our last MLFL talk for the semester, we have a very exciting guest, Yue Wang. He's a research scientist at NVIDIA Research. He graduated from MIT, working with Professor Justin Solomon. His research interests lie in intersection of computer vision, computer graphics, and machine learning. His paper, Dynamic Graph CNN, which is very famous in the community, has been widely adopted in 3D visual computing and other fields. He is a recipient of the NVIDIA Fellowship and is named the first place recipient of the William A. Martin Master's Thesis Award for 2021. Yue received his bachelor's degree from Zhejiang University and a master's degree from University of California, San Diego. He has spent time at NVIDIA Research, Google Research, and Salesforce Research. And please welcome Yue Wang.
Okay, thank you so much for the nice introduction, and most importantly, thank you so much for the invitation. My name is Yue, and I really feel excited, and I'm very glad to present my research on learning 3D representations with minimal supervision. And of course, when I say minimal supervision, this is broadly defined and includes much more than self-supervised learning. So without ado, let's jump to today's talk. So before we start, I want to tell you a story behind this device, the RealSense RGBD camera. So 13 years ago, Michael Brownstein, who is well known in our field, co-founded this company Envision to do facial recognition. So at that time, one use case they worked on was to tell identical twins apart with computer vision algorithms. So if you know Michael, he has a twin brother, Alex. So this is a very interesting use case for them as well. However, later they found this was actually a very challenging problem at that time. So they decided to take a step back and work on hardwares. This is because at that time, the hardwares they have cannot capture 3D geometry or specifically point clouds or depth images from the environment. And recognizing images or faces from 2D images at that time, it's quite challenging. So they started working on hardwares and built their own structured light sensor, which is this camera show here. Later on, this company got acquired by Intel, and this technology becomes what we now know today as RealSense. So several years later, Apple introduced a similar structured light sensor to the front of iPhone, which is the Face ID. So now we can use our iPhone to capture point clouds from our faces. And starting from iPhone 12 Pro, Apple further added another time-of-flight LiDAR sensor to the back of iPhone. This further improves the 3D sensing ability of iPhone. And then last year, there were 242 million 3D sensing capable iPhones sold globally. So that means we actually have lots of devices nowadays to capture the 3D data from our daily life. Another motivating example I want to show here is the self-driving car. So Waymo is Google's self-driving car team, and the self-driving car system relies on the LiDAR sensor, which is mounted on top of this vehicle. And this LiDAR sensor spins 360 degrees and capture point clouds like this. So basically, the perception system takes the point clouds as the input and performs 3D scene understanding, which could be later used by the downstream planning and the control modules. And also, last year, Waymo drove 630,000 miles in the US, which means this is 630,000 miles of point cloud data. So again, we have a lot of point cloud data available around us. We can even use our iPhone to capture point clouds from our daily life. However, if we look at point cloud models, they are far from pleasant. For example, on the left, I'm showing a ImageNet classification task, which is tackled by a simple ResNet. And with this simple ResNet, we can easily achieve almost 67% accuracy. And this is a 1,000-way classification problem. However, on the right, if we use the same neural network to take, for example, point clouds sample from this ModelNet 40 dataset, we only achieve 29% accuracy. Also, this is only a 40-way percent classification problem. And of course, I know these results are kind of out of date. This is more like a motivating example of why we want to study point clouds at the beginning of my PhD. So if you look at the gaps closely, so this means our 3D algorithms are not ready for many robotic applications. And these imperfect 3D algorithms will cause serious problems like this. For example, this is a car crash in the US 101 in California. And this Tesla car crashed into a white truck because later investigation showed that it didn't detect this rollover accident, and the object detection system basically failed at the time. So what are those gaps, and how can we bridge those gaps? So to me, there are at least 3 challenges in starting 3D data or solving 3D tasks. The first one is on the model side. As we all know, 3D data is sparse and unstructured. For example, point clouds are usually represented by a set of points, and while meshes are represented, triangle meshes are represented by, for example, a triangle soup. So these data are not regular and they are kind of unstructured. However, the models we develop in 2D domain usually takes 2D regular grids as input, which means these 2D models do not generalize to the 3D case. The second challenge is on the task side. As we all know, many perception tasks should share similar domain knowledge. For example, if we solve a depth estimation task, this should help solving optical flow or thin flow estimation task. However, many algorithms we developed in the 3D domain in the past were not machine learning based methods, which means these methods did not encode prior and they are not learnable. And finally, on the data side, 3D data is ubiquitous. As long as the self-driving car is driving on the road, we can capture unlimited 3D data. So we have lots of 3D data available around us. However, annotations are quite expensive. So think about how we enter 3D point cloud. We need to modeling the objects in the 3D space and put a 3D bounding box on top of each 3D object and manually do the adjustment. This is way expensive than, for example, labeling a 2D image. So that means 3D annotations are not that quite available to us. So basically, my past efforts focus on bridging the gaps by taking ideas from machine learning, computer vision, and computer graphics. So on the model side, we design 3D specific neural architectures, which are tailored for this irregular and unstructured data. And on the task side, we investigated learning-based 3D perception. So we want to combine traditional geometric perception algorithms with modern machine learning tools we have. And on the data side, we investigated 3D self-supervised learning, which could be seen as a way to tackle the data or the annotation issue. So my overall goal is to design 3D learning algorithms that understand geometry with minimal supervision. And before I jump to the main contents of today's talk, I want to set up some expectations for audiences. So first, I talk about 3D learning, my goal, which is 3D learning algorithms that understand geometry with minimal supervision. So I also talk about some background and motivations in previous slides, so which are In high level, we want to have some specific designs for 3D data, including point clouds and the multi-view images. And in the next step is I will present the geometric deep learning toolbox we have been working on for a while. In that regard, I will touch algorithms that respect geometry of data, as well as algorithms that leverage geometry as supervision. And then finally, I will talk about some perspectives and opportunities, and this will include some recent efforts I have been doing in the neural rendering domain. So specifically for today's talk, I will talk about 3 lines of research. The first one is how to incorporate geometry into 3D learning pipelines. I will use my past works as some examples to talk about how we incorporate those geometric inductive bias into 3D learning algorithms. The second line of research I want to talk about is how to encrypt geometric perception with learning. And in that regard, I will talk about some efforts on combining iterative closest point with some neural network feature extractor. And then finally, I will briefly talk about how we enable 3D self-supervised learning by leveraging supervision from data. And then without further overdue, let's jump to the first direction, how to incorporate geometry into 3D learning pipelines. So let's look at the example we saw at the beginning. So why is this so hard? Why there is a big gap between this image classification model and this ModelNet 40 classification model? Essentially, they are the same convolutional neural networks. So to me, the fundamental difference is that point clouds are not images. So if we look at how images are represented, they are usually represented by regular 2D grids. And in each position is a pixel, which is a combination of red, green, blue values. However, if we look at how point clouds are represented, they are usually represented by unordered sets. What do I mean by unordered sets? So we have a point cloud represented by this set, and then each element is a combination of 3D coordinates of a point. And if we change the order of this set, we get another set. Essentially, these 2 sets represent the same shape or same object, but they have different orders, and we can further permute the orders without changing the resulting shapes or objects, etc., etc. So this property breaks the fundamental assumption of the machine learning tools we use, for example, multi-layer perceptrons and convolutional neural networks, because these 2 neural networks usually assume we have a fixed order of input. So if we put this point cloud data into these 2 architectures, we will get different features if we permute the input orders. However, we know they represent the same shape. And this fundamental difference or challenge makes learning from point clouds with existing neural networks very challenging. However, if we look at the point clouds more closely, is it really unstructured? So if we stare at this point cloud, specifically this Stanford Bunny for a minute, we realize that it's not that unstructured because this data is generated by sampling from a continuous surface of a shape. So there is actually a structure out there. For example, the surface itself is a nice structure. It's just we don't know how to recover the structure and how to leverage the structure to enable learning. In computer graphics, one data representation we usually use is triangle mesh, which can be seen as a special type of general graph. And this graph-like structure provides several conveniences. The first one is we know the local connectivity between points, and this local connectivity induces some geometry, and we can use this geometry to enable learning. And the second, with this graph-like structure, we may use some existing tools developed in graph deep learning to enable learning from point clouds. So the question we want to answer here is, can we learn the features and reconstruct the graph structures at the same time? And can we use the graph-like structure to help machine learning? So to that end, we came up with this architecture, dynamic graph convolutional neural networks, or DGCN. In high level, DGCN takes point clouds as input. It tries to recover a graph-like structure in the latent space, and then apply graph convolutional neural networks on top of this graph structure. And with learned features, it further refined the graph-like structure. And the contributions of DGCN are it bridges geometry processing and graph deep learning. And it's also an unsupervised semantic structure discovery pipeline, which I will talk about in more details later. So let's look at DGCN in more details. So basically, DGCN takes point clouds as input. So let's use the word simplest point cloud as an example. Here I have a point cloud, which is represented by a set of points. For example, we have n points here. And we want to learn features for each point. Specifically, we want to learn the features for this central point SI. And to approximate the underlying structure, we actually use a KN graph. So that means we connect node J to node I if node J is among k nearest neighbors of node I. So basically, we just run a KN testing and make a KN graph. And then on top of this KN graph, we define edge features. And the edge features are the concatenation of features from two ending nodes. Then we use a shared multi-layer perceptron to further leave the edge features into high dimensional space, because at the end of the day, we want to use neural networks to learn features. However, this is still features defined on the edges, but we are interested in the features per point. So you can imagine we have a local pooling operator which pulls the edge features to get back the node level features. We basically do the per channel pooling over a local neighborhood of each point, and then we get back the per point features. And after we obtain the new features, we construct a new KN graph. And this new KN graph is different from the one we used in previous layers, because in previous layers, we construct a KN graph based on the input features, based on the input XYZ defined in the Euclidean space. Here, the new KN graph is reconstructed based on the feature distances. So we basically do a KN testing in the latent feature space and construct a new KN graph. And this new KN graph incorporates some non-local information, because once they are kind of far from each other in the Euclidean space, might be very close to each other in the feature space. And I will show some examples in next few slides. So basically, DGCN alternates between feature learning and the KN graph reconstruction. So this is the overview of DGCN. And if we look at the results, so basically DGCN achieved the state-of-the-art performance as of summation. Most importantly, compared to the CNN baseline, we have looked at in previous slides, DGCN achieves almost a 60% improvements by considering the geometry of data, or by considering the underlying structure. And if we allow dynamic graph updating rule. So we see another 3.8 improvements. And combined this this achieves almost a 63% improvement from a simple CNN-based supervised learning baseline. And this brings the model to almost 93% accuracy. And as I said, this achieved a state-of-the-art performance when we submitted the paper like 3 years ago. So another result I really want to highlight is the feature visualization. So basically, at the beginning, I said DGCN is capable of discovering semantics from data. And what does that mean? So that means we train a DGCN model on a point cloud classification task. So by no means DGCN can label per point semantics. However, we found that after training, DGCN can actually discover such per point semantics automatically from data. So here, let's look at some concrete examples. So here we visualize the feature distances in the latent feature space. So on the left, it's a feature visualization after the first layer, while on the right, it's a feature visualization after the third layer. So we basically select one red control point and compute the feature distances between this red control point and all other points. And the color denotes the distances. As you can see in the first layer, this distance still is more like a distance in the input Euclidean space. However, as we go deeper in the model, we see the distances is become different. So especially in the third layer, the points that are close to the red control point are not close to it in the Euclidean input space. However, they are actually on the same semantic parts of this object. So for example, points close to this red control point are on the face of this task. So this means DGCN is actually discovering such semantic similarity in the latent space. And this is surprising and intriguing because DGCN can be potentially used as self-supervised learning pipeline to enable learning from point clouds without or with minimal supervision. And that was DGCN visualization. And in addition to being a point cloud model, DGCN can actually summarize multiple frameworks in a single formulation. So if we write down the DGCN in the most general form, we can realize that many frameworks are actually special cases of DGCN. For example, we have a DGCN formulation here. So we want to learn features for node I, and we have these learnable parameters phi and psi, and the psi accounts for the message parsing from node J to node I, while phi accounts for the final feature generation. And of course, we have this permutation invariant operator, which aggregate the feature, which aggregate the local edge features and bring the edge features back to the node level. And let's look at some concrete examples. The first example I want to show is deep set and the PONET. So if we remove the message parsing from this formulation, we essentially get the deep set in the PONET formulation, because deep set and the PONETs operate by considering each point individually without considering the message parsing between points. And another example is that the very popular transformer models are special cases of DGCN if we have a complete graph. And I want to mention that DGCN is actually before transformers become popular in the vision domain. And then finally, if we are given a fixed graph, DGCN reduced to graph convolutions as we expected. So if we were to summarize DGCN, so DGCN is a learning task-specific graph for particular tasks. And also is a pipeline that performs latent graph learning, and that is closely related to manifold learning in the machine learning literature, because in manifold learning, we also want to recover the underlying structure of your data manifold. So beyond its direct usage in point cloud learning, DGCN actually see a lot of adaptations in other domains. For example, it's used in cellular modeling, disease prediction, and drug discovery. And of course, it's used in 3D object detection to help autonomous driving. And the most surprising thing to me is actually DGCN is widely adopted in high energy physics. So physicists use DGCN to tackle a problem called particle tagging, where the problem is to label particle point clouds, label each particle in a particle point clouds. And the DGCN has become a very standard model in that field. And I'm very glad the DGCN has a nice connection to this science research. So this is the first example of showing how we combine or incorporate geometry into 3D learning pipeline. So next, I want to show an example which is more on the application domain, which is 3D object detection. So although I talked a lot about point clouds, there are certain cases we don't want to use point clouds, simply because LiDAR sensors are expensive and they're not quite scalable. For example, Tesla has removed all its LiDAR sensors from its vehicles. And the only sensors they rely on are the multi-view cameras. But multi-view cameras brings in several challenges for 3D for object recognition for autonomous driving. Why is this more challenging? Let's look at some concrete examples. So here is a top-down visualization of a Tesla sensor setup. So as I said, Tesla only relies on the multi-view cameras to perform object recognition, and there are several cameras mounted on top of this vehicle. There are front-facing cameras, there are side cameras, and there are back-facing cameras. And let's look at one image that is captured by the front-facing camera. And this is the image. So the task here is to recognize all those objects and put a 3D bounding boxes, put a 3D bounding box on top of each object. So if you look at the truck in the middle, this is fully okay because we can almost see the complete truck. However, if we see the truck on the right, so this introduces several problems. So if we want to perform 3D object detection, that means we need to label a 3D bounding box for this partially observed truck on the right. So we need to infer this full 3D bounding box information based on this partial observation. This will certainly introduce several big challenges for 2D based detection models. The first one is, as I said, we only have partial observation, and it's really challenging or difficult for the 2D based detection models to infer the full 3D bounding box information. And another issue, more serious issue, is actually if we look at the images captured by another camera, so we see another part of this truck. And if we run the same 2D based object detection model, we will infer another 3D bounding box for the same object. So that means for the same object, we actually have multiple predictions. We have multiple bounding boxes for the same object. So that means during the inference, we need to aggregate those predictions and then remove these redundant predictions. And these post-processing steps are usually not parallelizable, and So it will definitely slow down the overall pipeline. And this is actually the issue that is seen by many common common 2D based object detection models. So for example, CenterNet and Focus 3D are probably the most popular methods that tackle 3D object detection from 2D images. Essentially, what they do is to take multiple 2D images as input and perform per image 3D bounding box prediction. And at the end of pipeline, they use post-processing step such as non-maximum suppression or NMS to remove or to aggregate those redundant predictions. So definitely they will have these two issues as we discussed at the beginning. So how can we solve this problem? So if we look at this problem from another view, for example, on the left, I put a visualization of the point clouds, but I want to mention that this is for visualization purpose only. We do not use point clouds in this architecture. So if we look at this object we saw before, we realize that if we look at this in the 3D space, there are actually only a single object. So the redundant problem arises because we have multiple parameterizations in different camera images. So if we can make a prediction in the unified 3D space, we won't have this issue at the first place. So this is actually the motivation of our recent work, Data 3D, which performs 3D object detection from multi-view images while 3D to 2D queries. So basically, the Data 3D starts with a set of bounding box queries, and you can view each bounding box query as a prior of bounding box prediction. And these priors are kind of learnable, and you can adjust those bounding box parameters with gradient descent. And for each bounding box, bounding box query, we have a reference point, which can be viewed as the center of a bounding box, and this reference point is decoded by a multi-layer perceptron. And you can, as I said at the beginning, these bounding box priors are defined in the space, in the 3D space, and therefore this reference point is also defined in the egocentric car coordinate system. So that means for each potential object, we only have a single parameterization for it. And based on the reference point, we project the reference point back to each 2D space. For example, we project this reference point to this camera front view and the camera of this front camera view and this front right camera view, and we query the corresponding features in the in each location, from each 2D images, and then we fetch the corresponding 2D features and put them back to the 3D space. So we aggregate the 2D features in the 3D space by doing per channel pooling. So finally, a bounding box prediction is made by a multi-layer perceptron according to the aggregated 2D image features. As you can see, this prediction paradigm only has a single parameterization for each 3D object. So that means we won't have this redundant issue at all, as we discussed at the beginning. And also, what is more important is now when we make a single prediction, we use the features from multiple views. This will definitely alleviate the occlusion problems, which are usually seen by many 2D based or single image based detection models. So let's look at some results of this Data 3D model. So on the left, I'm showing the 3D detection performance on the new scenes dataset. So basically, new scenes is a dataset that benchmark image-based 3D detection models. And here I'm showing the 3D MAP. And the two baselines we compare to are the popular CenterNet and the Focus 3D architectures. So as you can see, without any doubt, Data 3D achieved a better performance. And another important thing I want to mention is that no matter we add the post-process step, such as NMS, or remove this post-process step, Data 3D doesn't see any performance drop. So it's basically maintains the same performance. However, for CenterNet and the Focus 3D, if we remove the post-processing steps, you will see a lot of performance drop. This is because they rely on this post-process step to perform a prediction aggregation after making predictions for each single image. Another result I want to show is a benchmark on the camera overlap region. And here we compare Data 3D to Focus 3D. So overall, of course, Data 3D achieves better performance than Focus 3D. And what is more important is here, if we benchmark the performance for these two methods only on the camera overlap region, we see bigger performance improvement. This is because Data 3D utilizes the multi-view features to make prediction for each single object, while Focus 3D only takes each single image and make predictions based on each single image. And this is a result of Data 3D. And by looking at these two architectures, the takeaway message I really want to convey is 3D architectures should consider the geometry and operate in the 3D space. Although sometimes we have input defined in the 2D space, such as those multi-view images. So this was the first direction I want to talk about today. And the next, I would like to talk about the second direction, which is to equip geometric perception with machine learning. So geometric perception is a very classical problem. And the most classical one is perhaps point cloud registration, which is widely used in computer graphics and robotics. For example, in simultaneous localization and mapping, algorithms use point cloud registration as a way to aggregate points from multiple frames and fuse them as a consistent map for robot localization. And let's use point cloud registration as an example to talk about how we combine geometric perception with machine learning. So here, I'm showing a very simple example of point cloud registration. So we are given 2 point clouds, and each curve has 7 points on it, and we want to align these 2 curves. We want to align these 2 curves with rotation and with a rigid rotation and translation. And mathematically, this is defined by minimizing pairwise distances between these 2 point sets. And here, the parameters are the rotation R and translation T, and also the correspondence between these 2 points. Point sets defined by this sigma. So the most classical algorithm to solve point cloud registration problem is perhaps iterative closest point, or ICP. So the way ICP works is very straightforward. It has 2 steps. So the first step is the correspondence finding. So basically, given 2 point clouds, we want to set up the correspondence between these 2 point sets. And the ICP uses a simple nearest neighbor heuristic to set up correspondence. So in other words, for each point in point set X, it finds its nearest neighbor in the second point set and uses as a correspondence estimation. And the second step is based on the correspondence, it solves this minimization problem with a closed form solution to get the final rigid transformation estimation. So due to time limit, I won't go into the details behind these equations. So all I want to say here is, as long as we have a good correspondence, we can solve this minimization problem in a closed form and get the final rotation R and the translation T. However, although simple, ICP has several problems. For example, if we are given 2-point clouds like this, and the ICP will estimate a very wrong correspondence between these 2-point sets. And by no means ICP can estimate the final correct rigid transformation. In other words, correspondence estimation in ICP is purely geometric. There are lots of local minimal solutions. And also, there is no data prior. That means solving one registration problem doesn't solve other registration or doesn't help other registration problems. Because when we are given 2 new point clouds, we just solve them as a new problem. And this will require some task-specific tuning for the hyperparameters. So can we do better with machine learning? Can we use machine learning to help ICP? The answer is definitely yes. So to that end, we came up with the architecture that combines this ICP architecture with point cloud neural networks. So specifically, we have 2 point clouds, and we encode them using the DGCN networks we talked about in previous slides into feature space. And here on the right, these 2 point clouds become some featureized point clouds. And in the feature space, we set up the correspondence as we did in the ICP pipeline. So we use a similar nearest neighbor heuristic to set up the correspondences. However, the difference is that the nearest neighbor testing is done in the feature space versus the nearest neighbor testing is done in the input space in ICP. Because they are kind of neural network encoded features, they will encode some prior. However, is it differentiable? So this is a common question we ask when we design a new machine learning pipeline. It turns out this nearest neighbor correspondence is not differentiable simply because we use the indices of points to get the corresponding point features. And this will make this module not differentiable. So to solve this issue, we instead came up with a mechanism called software correspondence. So that means for each red control point, instead of getting the real point in the second set, we estimate a virtual green point, which is a weighted average of all the points in the second set. And the weights are based on the feature distances between all the points in the second set and the red point. And then after we have this virtual green point, we set up the correspondence in the feature space. And since this is a software correspondence, it's definitely differentiable, and we can train the whole architecture in an end-to-end fashion. So this is the overall architecture of the method deep closest point, or DCP. So basically, in high level, DCP takes 2 point clouds as input. It uses a DGCN as a feature encoder to encode those points into feature space. And in the feature space, we set up the correspondence. In fact, in the paper, we call it pointer generation because we want to generate a pointer from each point in point set X to a point in the point set Y. And after we have the correspondence, we can solve the previous minimization problem using the closed form solution we have seen before and get the rotation R and translation T. And since every module here is differentiable, we can train the whole architecture in an end-to-end fashion. Then let's look at some results of DCP. So here we compare DCP to many classical optimization-based methods such as ICP, Go ICP, and FGR. The Go ICP and FGR are some state-of-art variants of ICP. And also we compare to PointNet LK, which is a learning-based method. So as you can see, in terms of the rotation error, we achieve a lot of improvements over these baselines. Now also we test these methods, we benchmark these methods using unseen categories. This is to test the generalization ability of all those methods. As you can see again on the right, DCP achieves very strong generalization performance compared to other methods. Also, we have some visualizations. Here I'm showing two examples of applying all those methods to a guitar case and a human body case, human body shape case. And as you can see, for the human body shape case, all methods do a very good job. This is because human body shape doesn't have very sharp features, and they are all kind of smooth features. And there are not many like local minimal solutions. However, for the guitar case, because it has several it has a lot of sharp features, so many methods such as all other methods actually they suffer from local minimal solution, except ICP, except DCP predict the correct transformation. Now here on the right, I'm showing you how DCP improves ICP because it's known that ICP is prone to local minima, and if we can provide a good initial guess for ICP, this can help ICP to find the global solution. So indeed, with DCP providing a good initial guess, ICP can actually find the global optimal solution. And the building on top of DCP, we also have an architecture called partial registration networks, which tackles the general partial to partial point cloud registration problem. So due to time limit, I won't go into details of this architecture. So in high level, these architectures incorporate several additional improvements over DCP. So the first one is we use the iterative refinement mechanism similar to ICP to further improve the performance of DCP. And also we use a key point detection module to find the overlap region between partial point clouds. And we only align those overlap regions. And this is some efforts on combining geometric perception, specifically point cloud registration, with machine learning tools. And by looking at these two products, hopefully I've convinced you that learning can actually help geometric perception. And we are able to improve traditional or classical geometric perception algorithms with modern machine learning tools. Now, finally, I want to spend some time to talk about talking about the recent efforts on 3D self-supervised learning by leveraging supervision from data. So self-supervised representation learning is a pretty popular topic in the image domain, for example. So here I'm showing several examples. On the top left, it's a jigsaw puzzle. Paper. So basically, this paper uses jigsaw puzzle as a pre-text task to learn some representations, and they want to transfer the representations to a downstream application. And on the right is a split autoencoder paper, which uses autoencoding or reconstruction as supervision to learn the representation, or specifically the feature extraction in a self-supervised manner. And on the bottom left are some examples of recent efforts on contrast learning, which is perhaps the most successful and popular methods for self-supervised learning from images. And then in contrast learning, the high-level goal is you want to pull positive pairs closer while pushing negative pairs apart. So by doing this, by solving this problem, the hope is we can learn some general features that can be used for any tasks. And the reason I want to talk about this self-supervised representation learning from images is that I want to set up the general I want to talk about the general setup for self-supervised representation learning, and we follow the same setup in the 3D domain. So the question we want to answer is that, can registration be a pretext task for 3D data, like autoencoding and contrast learning for 2D data? So although I talk a lot about point cloud registration, and I haven't told you how we generate the data. It turns out the data generation is a very simple and straightforward problem. So we can simply sample a point cloud from our favorite ShapeNet or ModelNet collection, and then we can sample a rigid transformation from a uniform distribution and apply this sampled transformation to the sample shape X, and we now get another shape Y. Now suddenly we have a training pair with ground truth transformation. And with this training pair, we can train a DDCN model on this point cloud registration task. And we can actually generate a limit data like this and train the registration model using this unlimited data. And then we can further transfer the learned representation or the feature extractor, specifically DDCN feature extractor, to a downstream shape classification task, because in shape classification task, we have to label the shapes or the objects. And by doing this transfer learning, the hope is to reduce the amount of annotations that are required by these shape classification models. And indeed, we did some experiments in the partial registration network paper. So basically, what we do is we compare DDCN model with learned weights from point cloud registration to a DDCN model that are initialized with random weights. Here, I'm showing some comparisons under different settings. The first setting is Z/C, means we train and test the model using aligned shapes. And the second one, Z/SO3, means we train these two models using aligned shapes and test the models using shapes randomly transformed in SO3. And on the right, I'm showing on the right, SO3/SO3 means we train and test the models using randomly transformed shapes. As you can see, under all settings, the one with learned weights outperforms the one without learned weights. And the most importantly, in the Z/SO3 case, the domain gap, the performance gap is even bigger. So this means with this learned weights, the model is actually generalized better. So this is a very initial try of 3D self-supervised learning from point clouds. And recently, we also have a paper that learns representations from point cloud sequences. So basically, we are given a point cloud sequence, and we want to use this point cloud sequence to, we want to learn some features from this point cloud, from this large-scale point clouds. And the way we do this task is we first detect the moving objects from this point cloud sequence. And after we detect those moving objects, we put a bounding box estimation using some classical algorithm, and then propagate the bounding box information to all other objects, such as some static objects. And then we solve two pseudo tasks defined here. So the first pseudo task is a single frame motion simulation task, where we propagate the bounding box info annotations to each single point. And the second pseudo task is we basically perform a single frame based object detection model. So by solving these two pseudo tasks, the hope is the representation learned from this unsupervised task can help some downstream object detection, some real object detection applications. And also we have some benchmarks here. So we benchmark the performance on downstream object detection, and we basically compare to some existing methods such as point contrast and the depth contrast. So point contrast is basically you can view it as a variant of the point cloud retribution work I talked about in previous slides. And the depth contrast is basically doing the contrast learning in the depth space. As you can see, by considering the point cloud sequence, our method achieves much better performance on the downstream object detection benchmarks. So this shows that we can actually leverage the motion information to enable self-supervised learning from point clouds. And after seeing these two projects, hopefully I've given you some ideas of geometric correspondence is a strong supervisory signal, and we are able to learn some feature representations from data in an unsupervised or self-supervised manner. And this is the last line of research I want to talk about today. And finally, I want to quickly provide some future opportunities and some recent efforts I have been working on. So the first one is multimodal learning. So as human, we are able to perceive the world through vision, language, sound, and touch. What if we put these multimodal signals into our favorite machine learning hub? What kind of emergent intelligence can we get from this paradigm? So there are actually several immediate choice of multimodal learning. For example, in this filter 3D architecture, we basically combine multimodal signals to improve the robustness and the performance of object detection models. And another way to leverage this multimodal signal is to perform cross-modality self-supervised learning. For example, in the self-driving car case, we usually have point clouds as well as multi-view images, and then we can have a point cloud network to encode this point cloud data, and also have an image network to encode image data. And then we can do a contrast learning in the latent space by bring the features of the same parts closer while pushing the different features apart. And the second direction I'm currently exploring is to build a pipeline from perception to control. As you can see, my previous works focus on the perception side of robotics. However, for robotics, that has much more than perception. It has planning and control. So at NVIDIA, I'm currently helping to build some end-to-end differentiable stack for autonomous driving. And also recently there are some exciting works from colleagues in other institutes. For example, in this learning to jump from pixels paper, they build a complete pipeline that takes visual input and performs so basically they takes a visual input as input, and the robot dog is basically based on the visual input, it learns to jump from pixel based on the image features. And also in Amazon robotic challenges, the challenge is to ask people to design some end-to-end stacks for robot manipulation. And I think in the future, I will continuously investigating this end-to-end differentiable pipeline for all these like robotic applications. And another direction I'm currently heavily working on is learning to synthesize with minimal supervision. So in the past few years, neural radius fields, or specifically NeRF, has achieved a lot of progress in rendering. However, NeRF still relies on a lot of domain knowledge in computer graphics to perform image generation. So one question I want to answer is, can we learn such domain knowledge without any like annotations from data? So basically, can we use a transformer as a way to learn those domain knowledge in computer graphics and performs image generation without knowing volumetric rendering? And this is a recent submission to CUPR. And also, I'm working on some few shot learning for neural rendering. So we also have a recent submission to CUPR, and we investigate the few shot NeRF problem by looking at the frequency, frequency domain, or specifically the positional encoding. And finally, I want to mention my ultimate goal, which is to enable robotic intelligence to solve hard problems. So this will involve some hardware designs, and of course, this will involve some software development. For example, this will involve operating system, programming language, perception, planning, and control algorithms. And then finally, these robotic applications will lead to several problems for our society. And I hope to tackle those societal problems with colleagues as well. And then finally, I want to summarize a little bit what I've been talking about today. So today I talk about why is geometry important in learning from 3D data. And also I present my approach, which is to combine geometry with learning. And I present the geometric deep learning toolbox we have been developing with colleagues for years. And also I briefly touch some future opportunities or some current efforts I'm currently working on. And then finally, I want to emphasize my ultimate goal, which is to enable robotic intelligence to solve hard problems. And with that, I want to thank all my collaborators and mentors and advisors for their support during my PhD, and also during my work at NVIDIA and other institutes. And I also want to thank Toyota Research Institute and NVIDIA for providing funding support of my PhD. And thank you so much for listening, and I'm happy to take questions if we have time.
Thanks, Yue. Thanks, Yue, for the great talk. Yeah, we have time for a couple of questions. If you want to ask a question, go ahead. Sure, go ahead.
I have a question on the paper DCP. There was a
Deep closest point.
Yeah, deep closest point. There was an experiment where you ran DCP plus ICP.
Mm-hmm.
I want to know, how is that different from what DCP is? So when you ran DCP and then used those results for ICP, you just use the naive nearest neighbors to identify the correspondence?
Yeah, so I couldn't hear the question very clearly, but my understanding is that the question is, what's the difference between ICP and DCP? So specifically for ICP, so basically it has a nearest neighbor correspondent finding step and then solve the closed form solution, solve the closed form problem. So basically for DCP, the difference is that first it encodes point clouds into feature space. Then we set up the correspondence in the feature space. However, naively applying the nearest neighbor heuristic makes the architecture not differentiable. So one major difference is we use software correspondence between 2 point clouds, while ICP uses hard correspondences between 2 point clouds. This is the first difference. The second difference is basically we set up the correspondences in the feature space rather than in the input space, and these features should include some prior for point cloud registration. And another difference is ICP is an optimization-based method. It tackles, it doesn't have any learning at all. So basically, for each problem, it just optimize a little bit and solve that problem. However, for DCP, it's since it's a machine learning-based method, it's trained on a large collection of shapes or objects. So basically, hopefully it includes some prior for point cloud registration. And I think that those are the 3 major differences between DCP and ICP.
There was also a question about, like, I think you had 2 implementations of DCP, right?
So what is DCP plus ICP?
You know, the question was, what is DCP plus ICP? So you had.
Okay, I see. Yeah, so here I'm showing. So the reason I show this figure is basically ICP is known to be prone to local minima. So the reason why I have this DCP plus ICP is that we want to show that with DCP providing a good initial guess for ICP, ICP can find the global optimal solution. And the reason why DCP cannot find the global optimal solution is that in DCP, as we talked about in previous slides, we have this software correspondence. And this software correspondence will make the results blurry. So basically, the correspondence is always soft and can be exact. So that's why we have another like ICP on top of DCP to get the final global optimal solution.
Any other questions? Yeah.
So for the
Just speak louder a bit.
okay, so I think there's one slide showing that you use registration as a self-supervised learning method, right?
Right.
Yeah, so I'm curious, do you really need real point clouds? You could also use some very basic point cloud from, for example, Cubic or Sapphire, and will that also work?
Yeah, so here, that's a good question. So basically here, I'm showing how we use this registration on synthetic data as a way to learn the repetitions. And later we basically have similar ideas, and but we don't use this we don't use object-based registration as a pretest task. Here in this work, which is led by my lab mate Xiangru Huang. So basically, we aggregate the point clouds temporarily, and we basically do a registration between between multiple point clouds, and then we align those point clouds and detect the moving objects, and that detection stage is also like a point cloud registration or object level registration. And after we find those moving objects, we use those moving objects as some pseudo labels. Yeah, so yes, we are definitely interested in using registration for relay state data to enable self-supervised learning. And this is some recent efforts on it. And we are currently actively extending this work to achieve better performance for this real world applications.
Thanks.
Yeah, thank you for the question.
Any other questions? Okay, yeah, I think we're out of time. Thanks again for the great talk.
Okay. Yeah, thank you so much for the invitation, and I'm looking forward to those one-on-one meetings.
Sure. Yeah, I will start. I think first meeting is around 2, so I will start at, like, you just join the meeting.
Okay, sounds great. Okay, I'll talk to you then.
Thanks again.
Yeah, bye.
So I moved my monitor.
Yeah.
No, I moved my computer.
Uh,
Actually.